Hello, my name is Benjamin Joachimi, and I'm going to talk to you about the joint cosmological analysis of the weak lensing from the Kilo-Degree Survey and clustering from BOSS and other surveys. I am normally based at University College London, but I have, much in the spirit of this conference, done cosmology from home for the largest part of this year. What I'm going to talk about is very much a joint effort, and I list some of the key people here on this first slide, and some of whom will also give presentations at this meeting, so look out for those. I'm going to focus on the methodology of this analysis. So how did we get to these final results, and why can you trust them? And what you see here are the two key parameters that we constrain. We have S8, which tells us about the amplitude of structure growth. It's a derived parameter. You will see quite a lot in this presentation. It's defined down here. And omega matter, which tells us about the abundance of matter, mostly dark matter. S8 is very well constrained by weak lensing probes. You see that here in purple and pink. And clustering is very good at pinning down omega m here in blue. And it's nicely complementary, and you get these red constraints here. They're very good agreement. They're still tantalizingly discrepant with Planck, and you see the discrepancy is purely in S8, not in omega m, while at the same time we are consistent with previous analyses. For instance here, the similar analysis of the dark energy survey. Now, how we got to these results on the data is the subject of another talk. I'm going to talk about how we're going to get there. And so the schematic is as follows here. We are looking at these complementary probes, clustering and weak lensing in the same cosmic volume. For KiDS, we have tens of millions of faint galaxies, their shapes, which are coherently distorted by the intervening matter distribution through the weak gravitational lensing effect. And the same matter distribution is also traced by what we call lens galaxies. So galaxies whose 3D position we know very well from the BOSS survey, and also 2DF lens, which is a complementary survey in the south. In reality, on the sky, it looks a bit more difficult. So we see that here, KiDS is observed in two patches, one on the equator, one in the south, observed from Paranal. And you see these stripes also behind me here projected onto the pristine night sky over London. And we have almost complete overlap with lens galaxy surveys. In the south, that is 2DF lens in green, and in the north, it is BOSS. And we've got the much larger BOSS area here as well for clustering measurements on top. Now, all the gory details are in this paper referenced here. I can only give you now in the following some of the highlights that we looked into. Now, one is on the modeling, and here the key challenge is to combine the different philosophies of weak lensing, which goes deeply into the nonlinear regime and uses non-perturbative modeling of power spectra, in this case a halo model power spectrum, and clustering, which traditionally uses perturbation theory and perturbative galaxy bias terms. And so we have to make sure they're consistent. Here we see this for the matter power spectrum, and we compare this to the well-known Cosmic EMU emulator power spectrum. And you see there's good agreement within a few percent over the range of validity. For our halo model on very small scales, we also have the benefit that we can model baryonic feedback, so redistribution of matter through baryon physics. The amplitude of it is still very uncertain, and we marginalize over this amplitude, and you see the range within our prior given here. Now, it becomes really complicated then when we combine the lenses and the sources in galaxy-galaxy lensing, and we choose a hybrid approach. First of all, we use an emulator for the perturbative terms. That gives us orders of magnitude speed up in the modeling, but also it allows us to extrapolate a little further where perturbation theory would break down. And we also replace the perturbative nonlinear matter power spectrum with the halo model one. And that turns here from this orange line, and the deviation here from 1 tells us the nonlinear galaxy bias, to the gray line. You see this nice, smooth, and a consistent expansion. Yet, we cannot include additional flexibility, we don't know how, in the galaxy bias modeling, and so we still downweight and remove data vectors that would have significant sensitivity to this gray area here. Now, on top of that, our model also includes intrinsic galaxy alignments, which mimic the weak lensing, and also magnification bias, which is a weak lensing effect that modifies the lens galaxy samples. Right, moving on to the summary statistics for weak lensing that we use. Traditionally, that would be correlation functions. However, we measure those, but then derive Fourier-based band power spectra from those. So why this complicated step? Well, we get the best of both worlds. So we inherit from the correlation functions the insensitivity to the complex survey footprint, but in Fourier space, we have got a much more compact response that is shown here. So you see in L scales, these are the bands, and you see we nicely trace the actual scales of these bands in the underlying power spectra. On top of that, we get very good separation between E modes, which have all the cosmological signals, and B modes, which we use for systematics. You see the mixing here between those two is very small. We shall see later that we also have nicely Gaussian distributed properties of these band powers, and we get a bit of data compression, at least by a factor 2 over the correlation functions. Now, for BOSS, the 3D clustering, we just adopt their full shape methodology, and in this case, we use the correlation function wedges. Now, to test all our analysis pipeline, we need simulations. And instead of using expensive n-body simulations, we opted for fast approximate simulations, and many of them. So we can, for instance, also assess the very large variance covariances that occur in this case. So we use Flask to generate log-normally distributed dark matter in shells already. Big lensing is then simply given by integrating along the line of sight. Flask has the additional benefit that we can essentially define what 2-point statistics we want in these shells, and so we can use this very well for validation in this case. Now, we complement this with a new code called Salmo that then populates these matter distributions with galaxies according to the actual survey properties, and that applies to the footprint, but also to number densities. And what is new is we not just get these survey properties right globally, but we get them right in each individual point in each line of sight. So we have spatial variation in there. And we can make this fast to a point that the mock creation now is much shorter than the actual analysis of the mock data sets. And that allows us to make more than 20,000 of these initially full sky mocks. Now, speaking of the spatial variation, it's simply a consequence that we've got different observing conditions. So on one night, you observe slightly deeper into the universe than on other nights. And that has consequences. For instance, if you observe deeper, your redshift distribution will shift somewhat to higher redshifts. You just look deeper into the universe. The number density of galaxies will go up. You see more faint galaxies now. And even the distribution of galaxy shapes changes in a very complex and non-obvious way, and that determines the noise properties of the weak lensing. All of these are now taken into account, and we can assess them with our mocks. Now, looking at the covariance matrices now. So with many mocks, we can calculate covariance matrices, and what you see here are actually correlation matrices. We look at the variance in a moment. You see here clustering statistics, galaxy-galaxy lensing, and cosmic shear, and the little boxes are different tomographic bin combinations. The takeaway message on the left-hand side is in these highlighted boxes here, that's the cross-correlation between the BOSS clustering and the weak lensing signals. And as you can see, these boxes are essentially empty apart from a bit of noise here. So that means that BOSS, to very good approximation, is independent of the KiDS measurements. So we can just treat BOSS separately, use the BOSS collaboration covariance matrix as is, and focus on the weak lensing side. Doing that, we have a fully analytic model of the covariance, and that's shown here in the top right, and the corresponding elements here from the mocks down here, and you see very good agreement between the two. You also see that generally the cross correlations are small. That's another benefit of our Fourier space statistics. Now, looking at the default analytic model in more detail, of course, it gets very complicated very quickly. So the main takeaway from this busy slide is it looks quite colorful. And the different colors simply are the different contributions. So in yellow, we have noise. In red and orange, we have sample variance contributions. Purple and green would be non-Gaussian contributions on top. And in gray, we have the uncertainty of our shear bias calibration propagated into the covariance. On the left, you see a few examples, select elements of the covariance matrix, and you see that often several terms are important and relevant to these. And using the largest one in each, we color the elements here on the right. So you see the dominant term for each covariance element here. Yellow, noise, dominating on the diagonal. And on the off diagonal, you again have a very broad mix. All of these you need to get right for a proper analytic model. Now, what happens then when we have the realism of spatial variations in the surveys there. So again, it's a very busy slide. Just take away the sort of gist of it. On the left-hand side, we have the mean, so the 2-point statistics themselves. On the right-hand side, we have their standard deviations. The different panels are again the different tomographic bin combinations. The top 2 rows are galaxy-galaxy lensing, and I've blacked out the ones that we do not use in the end. And in the top, the bottom 3 rows, we have cosmic shear. So for the signal, we have a few percent level effect when we go from a sort of very simple homogeneous survey to a realistic footprint, and you see the largest effect, for instance, around here, which is 3–4%, and that was seen in an earlier paper as well. That is fine for us, so we get away with not taking this into account, but it's very clear that in future, these analyses will have to take this into account. They cannot take global summary statistics over the whole sky anymore. The effect, as expected, is much stronger on the error bars. If you've got additional variability, you increase the overall variance, and that can happen by up to 20% or even just beyond in the standard deviation. Now, the good news is that our analytic model captures these quite well. So in red, you see the effect on the MOCs, and in blue, you see how well the analytic model traces this, given our input survey characteristics. It works very well for cosmic shear. For large scale, so low L in galaxy-galaxy lensing, it doesn't work that well. We understand why, and it doesn't have an impact on our cosmology just yet. Right, moving on more to our likelihood analysis. One important message is there's no such thing as uninformative priors. So this is illustrated here in these 2 examples. We have here the key cosmological parameters, their posteriors in blue, and their prior distribution in red. Surprisingly complicated. So the sampling parameters here on the left were those of the DES year 1 cosmic shear analysis. They use AS, so the primordial power spectrum amplitude, as a sampling parameter with a top hat prior. On the right, we have the analogous case for earlier KiDS, KV450 analysis, where they use log AS with a top hat prior. And what you see here is that, for instance, the length of the famous cosmic shear banana, so the degeneracy between omega m and sigma 8, is almost completely determined not by the data, but by the priors. So the prior that DES chose in a highly non-trivial way translates into a somewhat tighter prior here in this plane, and hence the banana is shorter. You see that in S8 also, the prior is actually anything but flat. Fortunately, in a regime where we have non-zero likelihood, it is roughly flat. However, to avoid all these issues, we now impose a wide top hat prior directly in S8. Now, with our many MOCs, we can actually look at the sampling distribution of our summary statistics and test whether they are reasonably approximated by a Gaussian, because we want to use, like everyone else, a Gaussian likelihood. Now, on the left-hand side, we see this for our different data vector elements for the band powers. On the right-hand side, it's for the traditional correlation functions. Blue means we are nicely consistent with a Gaussian marginal distribution. Red means not so much. And we see for band powers, we're actually fine. Whereas, as I've seen before, on large scales for correlation functions, we do see a deviation from Gaussianity, and that's simply because the correlation functions have very broad sensitivity. They also pick up some sensitivity to very low multipoles, which are non-Gaussian, and that is reflected here. In a similar spirit, we can also look at the actual sampling distribution of our goodness of fit statistics. So in this case, the minimum chi-square, and that is shown here. Now, classically, probably all familiar with the reduced chi-square as a measure of goodness of fit, but if you look into the details, it's only applicable if your data is normally distributed. Well, that's sort of okay for us. If your model parameters are linear in that model, certainly not the case for us, and the priors are informative. Also not true. We have a lot of informative priors in our data set. Now, fortunately, it turns out that our sampling distribution is still very well modeled with a chi-square distribution, and that's the blue and red lines here in this case. However, that free parameter that you still have, which is the mean or the degrees of freedom, is not what you would traditionally expect, which would be the number of data minus the number of parameters. Here we've got the actual number of parameters in 2 cases of our analysis. And if we look at the actual mean, we can derive an effective number of parameters, which is about just over a factor of 2 smaller than that. And that makes perfect sense, because we have a lot of nonlinear degeneracy, so these parameters are anything but independent. And also we have informative priors that essentially limit the wiggle room of these parameters. And so this should be taken into account when assessing the goodness of fit. And then another important question is, how do we report parameter constraints? What you expect from us is a single number for, let's say, S8 with error bars around it that represents our best guess of what that parameter really is. Now, traditionally, what you would do is you look at the marginal posterior of these parameters and then report the mode or the mean and an associated interval that's shown here in blue, which gives us sort of the highest 68% for 1 sigma region of that posterior. Can also work from the tails, gives a very similar answer. Now, there's a slight issue here, and you see that here, in that the 1 sigma regime doesn't even contain the true value of this mock analysis, which is actually the blue dashed line here. Now, that doesn't mean that our analysis pipeline is wrong. It's just a projection effect from our very nonlinear high dimensional posterior. If we look at the multivariate maximum posterior, it actually is bang on. So it's shown here by the orange star. So this is what we call the map, the maximum posterior. So in addition to the traditional way, we now also report this map value, and we design a new credible interval that is designed to encompass the map for sure, and it reduces to something intuitive, as you would expect for Gaussians and 1D distributions. And this is shown here in red. It's derived by a projection of these highest posterior values, which are shown in red. Okay, so if we now look at our actual constraints here, you see 2 bars. The solid ones are this new measure around the map, and the traditional one is shown here as dashed lines. And the case that we looked at was this one. So you indeed see the traditional one is shifted off from the true value given by the dashed line here, whereas the solid lines safely encompass always the true value. And you see the benefit from probe combination here. CS would be cosmic shear, this would be clustering, this is galaxy-galaxy lensing. And you see that the effect of that shifting is strong when we have the galaxy-galaxy lensing end, which has low constraining power, but many new parameters to take into account. And in our case, the galaxy-galaxy lensing is relatively poor in constraining power just because it's overwhelmed by the much larger area that we have for clustering from BOSS. So that wouldn't be the case if you do the same survey, 3 times 2-point analysis. And you see the benefit of shrinking these edge constraints when you combine all 3 together. Now, also, we see when we use a mock or analytic covariance and look at the various survey effects that our results are absolutely robust to that. So we're clearly safe, we understand our covariance well enough in this case. And if we look at priors, you see that our SS constraint, so this is these 2, is a little wider in terms of the posterior that we get. So we're a little more conservative, which is a good thing, I assume. However, we again fully consistent, and also other prior choices in this case for the redshift distribution uncertainty have very little impact on our constraints. Right. So to summarize, I think that a main point here is that our constraining power on S8 for the 3 times 2 point now matches that of the 2018 Planck legacy analysis, and that's shown here. You see here the purple and the red would be Planck, this is us, and the width of these are now absolutely comparable. And if you go back to the real data constraints from the start, indeed that is confirmed. So we are as constraining as Planck. And also we can show that all known systematic limitations are controlled to about 1/10 of a sigma in S8. So that means our analysis is robust. These are the key takeaway messages. Now, what's next? KiDS isn't over yet. We have more data to analyze, and we have the aim of further improving our calibration of the redshift distributions and push deeper where we've got high signal to noise weak lensing signals waiting for us. And so that should improve our constraining power. We clearly need to understand the intrinsic galaxy alignments better. That's not a KiDS problem. That's a problem for all weak lensing surveys, and it's a challenging one to do this right for the faint and distant galaxy samples that we use for weak lensing. Related to that, we are in the process of developing a comprehensive halo model that includes the nonlinear cosmology, as it does already, but also the astrophysical signals, including the intrinsic alignments. Clearly, as we've shown, in future, we also need to improve our modeling of these spatial survey variations. They need to become part of our analysis. And this is a nice example of how we will have to translate increasingly our methodological insights to the next generation surveys. And on the weak lensing side, that's clearly Euclid and SST coming next, but we also have new interesting lens galaxies being provided by DESI, Foremost, and other surveys. So there's still much to do. Now, I leave you with a list of the resources and the papers that I've talked about, and I'm looking forward to your questions and hope to see you at the KiDS 1000 discussion session. Thank you.